Yeah, I would like to thank you all for hosting me. Your generosity during this trip has been incredible, and I want to especially thank Danielle for taking Mario and me around to introduce me to the beautiful country and all of the natural hazards and the communities that are impacted by those hazards. Today's talk is going to be about one of the hazards that both the United States and Ecuador have in common, and that's subduction zones. The work I'm going to present today is mostly focused on the Cascadia subduction zone. This is in the northwest part of the continental United States near the states of Seattle and Oregon and Northern California, where the Juan de Fuca plate is subducting beneath the North American plate. We're interested in subduction zones because they create huge earthquakes, huge tsunamis, but they also present very interesting scientific questions. In particular, Cascadia was one of the subduction zones where the phenomenon of episodic tremor and slow slip events was discovered. It's a region, at least in Cascadia, it's a region that's down dip, deeper than the seismogenic zone. And this region hosts approximately annual slow slip events, so slow earthquakes that don't produce many seismic waves. And so in this talk, I'm going to present earthquake cycle models, so models of earthquakes over thousands of years. And the goal will be to understand what controls, well, I'll tell you in a second. The goal will be to understand what controls the large megathrust earthquakes, but then also what creates slow slip events and their relation to the large hazardous earthquakes. So the models that we do are earthquake cycle models. We will take a subduction zone like this, take the plate interface, create a mesh like this, and then we solve the elasticity problem. So for the deformation of the rocks that surround the fault, and we combine that with friction laws on the fault, and we load the system very slowly, and then the fault slips in consistency with the friction law and elasticity. This is an example of the type of simulation that we do. You're looking at V is the slip rate on the fault, how fast the two sides of the fault are sliding. It's in a logarithmic scale here. This is a large megathrust earthquake that's propagating along the entire margin. There are also some smaller earthquakes that are limited, in this case, to towards the ends of the fault. These earthquakes occur spontaneously. We don't prescribe how and where the earthquake slip occurs. It's part of solving part of the problem. The goal, the reason that we do these is to study certain scientific questions. In this talk, I'm going to focus on the depth-dependent slip behavior. Why do we transition from megathrust earthquakes that create tsunamis to slow slip events? And you'll see it's a little bit more complicated in Cascadia. Another motivation for doing this work, another use, is to look at along strike behavior, segmentation. And I understand in Ecuador that's also an important problem. There are some patches of slow slip. Do those serve as boundaries for the large megathrust earthquakes and limit their size, or can a megathrust earthquake propagate through slow slip regions? So the type of modeling that we do here helps answer those questions. Part of what we'll do that is, I think, unique in earthquake modeling is we're going to focus a lot on connections with geology, metamorphic petrology, and fluids. Fluids are thought to be extremely important in subduction zones, but until recently have not been part of earthquake modeling. Fluids in a subduction zone come primarily from the subducting oceanic slab. So as the slab is being subducted, it has a structure with sediments on the top, basalts, gabbro, and then going down into the upper mantle. And these rocks have some water bound in the mineral structure, and that water is released during metamorphic dehydration reactions. That fluid release happens at various depths, and it's thought, and there's geologic evidence, that these fluids are transported up along the plate interface. Some of the fluids do ascend into the overriding plate, but a lot of the fluids migrate up along that plate interface. The geology shows us, in addition, like I said, the fluids are sourced by the metamorphic dehydration reactions, particularly from the basalts. It's also from compaction of the sediments in the shallow part of the subduction zone. I'll mainly focus on the deeper part. And then the other thing that is seen in the geology is that a lot of the deformation motion between the plates is accommodated within this upper sediment layer. So slip deformation localizes in that region. The ingredients to earthquake cycle modeling include at least elasticity, the deformation of the solid, the building up of strains and stresses, and friction. Friction, if we look at the actual rocks, we can see localized deformation. This is brittle deformation in the sandstones, so in the sediments that are exposed in Japan. We can see localized deformation. This is in the seismogenic zone. And so we're interested in friction along this surface. The rocks on either side are saturated in fluids, primarily water. And so the friction laws that we use, the shear strength of the fault is the product of the friction coefficient and the effective normal stress. This is the difference between the compressive stress squeezing the fault together and the fluid pressure that's pushing against the walls of the fault. And so you can have changes in frictional strength, not only from changes in friction, static friction, dynamic friction, we're used to thinking about that. You can also have changes in fault strength, which affect slip from changes in fluid pressure. And that's going to be one of the most important things that we study. In these models, we use a type of friction called rate state friction, where this friction coefficient evolves towards a steady state value that depends on the slip velocity. It's logarithmically dependent on slip rate. And this A minus V parameter, it can be determined from laboratory experiments. If it's positive, we call that velocity strengthening. The faster you slide, the more friction there is. And so that tends to create aseismic, more stable slip. And if A minus B is negative, and it is for many rocks in the seismogenic zone, then the frictional resistance decreases as the fault begins to slip faster. And that can create earthquakes and instabilities. The other thing that's really important and has not really been accounted for in earthquake modeling is that it's not just friction. As you go deeper and the rocks become hotter, it's not just this local deformation between the plates is not just frictional sliding. The rocks on either side actually begin to flow viscously. And so the fault, especially at depth, transitions into a broader viscous shear zone instead of localized frictional slip. And so we'll build that in to our models. In subduction zones, the physical process that allows that viscous deformation is known as pressure solution creep. So you can think about, and we'll idealize this process with a shear zone of a constant width W. Think about this as being a few hundred meters. And when you apply a shear stress, this whole region is going to shear somewhat uniformly. And so we'll use a viscous flow law that's a relation between the viscous strength and the strain rate, gamma dot, which is just the slip, sort of the overall slip velocity spread out over the width of this region. And there's a coefficient, which is the viscosity, and it's dependent on temperature. And so the viscosity decreases as you go deeper and the rocks become hotter, so it's easier to flow. There's a lot of geologic evidence for viscous flow, not only below the seismogenic zone, but even in part of the seismogenic zone. And most of that viscous flow is happening in very fine-grained rocks like mudstones. And so we use viscous flow laws that were developed for this type of rock. Pressure solution creep involves fluids is also important here as individual grains come into contact. Minerals like quartz or calcite dissolve in the water and then are transported to lower stressed contacts through the fluid and then precipitate. And if you do that a lot at the grain scale, you actually accommodate motion like that. And so that's the evidence that the geologists see. Now, the scientific questions that we're going to answer or attempt to answer are the following. So if we're looking at the upper 80 kilometers or so along the plate interface, in Cascadia, the upper part is almost fully coupled. So it's locked between earthquakes and it accommodates motion by large megathrust earthquakes. There's a region down here where there's slow slip events, and most of the plate motion is accommodated in slow slip events. Below that is steady creep, just at a constant rate, and that's happening within a ductile shear zone, so that's viscous flow. But then Cascadia also has a very mysterious region. It's a gap that separates the seismogenic zone and the slow slip region. The science questions that we're interested in are the following. So a large megathrust earthquake that happens, it's certainly going to rupture the seismogenic zone, but will it also go down into the gap? Will it go down into the slow slip region? So can large earthquakes propagate in regions that had slow slip? So I think that's a question that's also important for Ecuador. The other question is, how does this gap accommodate plate motion? Is it frictional, or is it viscous, or is it some combination of both of those? And also, simply what causes slow slip events? They were discovered almost 25 years ago, almost 25 years ago, but I don't think there's still a good understanding of what causes them. In Cascadia, the slow slip events occur at depths of about 30 to 45 kilometers. If we look at the long term, if we take multiple slow slip events, and these are commonly seen in geodetic data, so GPS or GNSS data, and we look at the long-term motion or velocity accommodated by slow slip events, that's plotted here in the color scale. And so you can see it's occurring mostly inland from the coast. So that's the slow slip region. We don't have any historical earthquakes. Earthquake were recorded in Cascadia. The last large megathrust event was in 1700, and it was so from paleoseismic studies along the coastline of forests that were submerged, and also some tsunami records. There's some constraints that are placed on the distribution of slip, and that slip is mostly offshore. It tends to stop right around the coastline. Whereas if you look at the slow slip events, that's occurring inland, and it leaves a gap between these two regions. And so that's the gap, and no one quite knows what's happening in that region. Okay, now I'd like to step back and discuss friction and viscous and how do we know whether material is going to deform friction, with frictional slip or viscous flow. So this is the friction-viscous transition or brittle ductile transition. And I'll first present the classical way of thinking about it, and then I'll suggest a new way that I think that we need to think about it. So if we look at depth here, and this is stress or pressure, I'll plot both of them. The normal stress on the fault increases with depth. That's primarily set by the weight of the rocks above it. The fluid pressure increases with depth. And so the difference of these, the effective stress increases with depth. So for a constant friction coefficient, the frictional strength increases with depth. Temperature also increases with depth. And so at some point, the viscous flow the viscosity decreases and it becomes easier to flow. And so we draw a viscous strength like this. And then the classical way of thinking about this frictional viscous transition or brittle ductile transition is to assume that it's whatever the weaker strength is. And so this is the depth at which that transition occurs. Now, we need to get quantitative. And so we can plug in numbers. The normal stress is the weight of the rock. So we take the rock density times gravity times depth. But what about pore pressure? So you could assume that it's hydrostatic. So it's just the weight of the water column. If there's fully connected pathways of water with no flow, then you would have hydrostatic pressure. But you get way too strong of a strength if you do that. Instead, there's strong evidence that fluid pressure is much higher than hydrostatic, and it's commonly parametrized in this way. So the fluid pressure is assumed to be proportional to the normal stress, and this proportionality factor, lambda, is just taken to be a constant. Now, there's not a really good reason for that, but it's a simple parameterization. It was introduced in the 1950s, and it's still widely used today. So we need very high overpressures, lambda values of 0.9, to get effective stresses in the range of 40 megapascals multiplied by friction coefficient of about a half, and that's a shear stress of about 20 megapascals. And there's lots of constraints, lots of reasons to think that that's about right. So there's evidence for really high fluid pressures, much higher than hydrostatic. I'd argue that we've spent a lot of time in earthquake physics thinking about the physics of the friction coefficient, but not enough thinking about fluid pressure and controls on fluid pressure. We're still largely using this model introduced in 1959. And so my group's efforts have been aimed at understanding fluid pressure better. And I'll show you that when we account for the processes that control fluid pressure, this is not the way that the frictional, viscous, or brittle ductile transition occurs. We don't have frictional strengths that are much, much larger than viscous strengths at depth. I'll show you models like this. This is strength, this is depth, so it's sort of a rotated version of this. Frictional strength occurs here. It does not increase linearly with depth. It starts that way, but then it becomes relatively constant. And then this is that frictional viscous transition. The viscous strength is shown in red, the frictional strength in blue. You'll see that they're almost exactly the same. And I think there's really good, compelling reasons for that. So these strengths are almost the same, which actually makes it very easy to switch back and forth between friction and viscous. And I'll show you that, why I think that's important. In addition, it's not an abrupt transition like this model would predict. Here, what's being plotted here is the fraction or the percentage of deformation that's accommodated frictionally in blue. So if all of this is blue at some depth, it's all friction, all orange, it's all viscous. But there's a broad region here over almost 20 kilometers in depth where it's a mixture of friction and viscous. And that's what the geology indicates. So to understand fluids, we need to think about the equations and the processes that control fluid pressure. Fundamental part of that is Darcy's law. So the fluid flux is proportional to the gradient in pressure minus the weight of the fluid. This is a lot like heat conduction. Heat flows from hot regions to cold regions. Here, fluids flow from high pressure to low pressure. That fluid flux depends also on properties of the rock, the permeability, and properties of the fluid, its viscosity. Now, let's try to understand from Darcy's law what a distribution of fluid pressure would look like. So if we assume that the fluid flux is constant and that the permeability and viscosity are constant, everything in this equation, all of these are constants, so we can solve for the pressure gradient and then integrate. And we get pressure is linear in depth. Part of that is hydrostatic. But then if you have fluid flow, you have to have a larger pressure gradient to maintain that fluid flow. the fluid is viscous and you have to push it through small pores in rocks. And so it takes extra pressure. And so we see that overpressure and fluid flow are closely related. Now, that was just assuming constant fluid flux, constant permeability. What really controls those? And so I'll look at that in a second, but first we're going to think about fluids. Where do they come from? Like I said, there's water that's bound in the mineral structure. In California, very close to where Mario and I live, are rocks like this. These are blue schists. These have a large amount of water bound in them. These are hydrated basalts. And as these rocks, as the rocks are subducted, they move through temperature. They go to increasing temperature and increasing pressure along some pathway that goes through different metamorphic facies. And the chemical composition of the rocks does not change, but the minerals change. And what's shown in the colors here is the amount of water that's bound into the mineral. So rocks might start out in the shallow region with maybe 5 or 6 weight percent water, but then they dehydrate. They go to 3% here in the green schist facies, epidote, amphibolite, another big dehydration reaction as they go into amphibolite eclogite. So these are the dehydration reactions that occur. Then the fluids migrate along the plate interface, and some of them might go upwards into the overriding plate. We're not talking about a large amount of water. So the amount of water, the fluid flux is about, when I give this talk in California, I can say it's comparable to the rainfall in California. Here I have to say it's it's 1/50th of the rainfall that you have here in Quito. So it's a small amount of water that's moving up. In our models, we're going to assume that the fluids are coming from the subducting oceanic plate. They move upwards along the plate interface. They move up to the plate interface and then move upwards. So we're going to try to get quantitative here. And this, I guess I'll show it like this. So in collaboration with a metamorphic petrologist, Kaylee Condit at the University of Washington, she takes a composition for the mid-ocean ridge basalt, drives it through the pressure and temperature pathway of Cascadia, calculates how much fluid is released, and then we take that fluid and then we just integrate from depth all of the fluid that has been produced below that, right? And assume that that all comes up. And so the fluid flux, if we put it in a channel of some thickness, and we'll use about 300 meters, that's constrained by the geology, and it's the upper 2 kilometers or so of the subducting oceanic crust that contributes fluids, we get a fluid flux that looks like this. There are large jumps in fluid flux at certain depths, and those are large dehydration reactions when rocks cross from one metamorphic facies into another. The number here, like I said, this fluid flux, it's similar to 1/50th of the rainfall that occurs here. Okay, now we need a model for permeability. So that's the fluid flux. Now we need a model for permeability. Many experiments show that permeability depends on effective stress. In particular, if you increase this confining stress, then you squeeze the pores, make them smaller. If you increase the fluid pressure, you make the pores larger. And so that changes permeability. And this permeability is seen to depend exponentially on effective stress. So this sensitivity can be constrained by lab experiments. In addition, there's 2 other processes that are important. As we deform the rocks, especially with brittle deformation, so frictional deformation, then we increase permeability. We create cracks in the rocks, we open the pores. So permeability increases with frictional slip. In addition, there's chemistry. This is especially at great depths, there's mineral precipitation, the cracks are closing, and so that's decreasing permeability. And so we'll introduce a model here where we account for both permeability increases with slip and permeability decreases from these healing or sealing processes. And we have the latter, the permeability decrease, the healing, occur over some time scale, T, and that depends on temperature, and it becomes shorter at depth. So if it's hotter, you can quickly precipitate minerals, you can seal and reduce the permeability. Under steady state conditions, we get some expression like this. Okay, so stepping back, we have now a model for pore pressure, effective stress, fault strength, both frictional and viscous. I'm going to show results first under steady state, so that it's not changing in time. And then I'll show you earthquake cycle modeling like the one at the beginning. So we're going to take pore pressure from our fluid transport model, and then we're going to have permeability depending on frictional slip. So then we need to have a model of how to partition, to split the plate motion between friction and viscous. So we assume that we have frictional surfaces inside a zone that could deform viscously, so we can have both friction and viscous. This is only a few hundred meters wide, so the shear stress is about the same. And so we have the total velocity, the plate velocity, split between friction and viscous, but they both, the viscous strength and the frictional strength, are the same. So we use a viscous flow law, a friction law, and put all of that together. Let me skip that. And when we do that, here's the results of the modeling. So what's shown here is the effective stress versus depth, either depth or horizontal distance from the trench, and this is for Cascadia. And we have the effective stress increasing linearly with depth, becoming constant, and that's actually due to that sensitivity of permeability to effective stress. And then the viscous deformation starts to become important, and so the strength starts, or actually, this is the strength here, the strength starts decreasing. Here in red is the viscous strength. So we go that from friction to viscous, and as frictional strength decreases, actually also, as the viscous strength decreases, then viscous strength and pore pressure also change. So in a way that these strengths are the same, and that means that effective stress decreases, right? Fluid pressure starts increasing and becoming almost lithostatic. And then, as I said before, the model has a broad region, 20 kilometers depth, where there's both friction and viscous deformation occurring. So that's the steady state model, but it doesn't make any predictions about whether the frictional slip occurs in earthquakes or occurs in slow slip events or occurs through steady aseismic deformation. We'll do earthquake cycle modeling to look at that in more detail, but first let's just assume, I want to test this prediction that we have a broad transition between friction and viscous. And so we'll assume for now that all of this frictional region occurs seismically. So between earthquakes, this region, this amount of, this is locked, or it's fully locked near the surface and then partially locked here. So during the interseismic period between earthquakes, there's viscous deformation that's accommodating some of the motion. Inversions of geodetic data in Cascadia show something very similar. So this is a map of coupling. So coupling of 1 means it's fully locked. Coupling of 0 means it's sliding at the plate velocity. And so you can see most of the region offshore is locked. And then there's a gradual transition to 0 coupling at depth where everything's just creeping at the plate rate. And that looks a lot like what this model is predicting. And so in that interpretation, this region of partial coupling is viscous flow, but then there'll also be frictional slip here. And in pink, you can see the regions of slow slip. So we need slow slip to occur in a region that at least some of the time can deform viscously. Okay. So now I want to turn to time-dependent models, earthquake cycle models. In these models, we're going to take the pore pressure and effective stress from that model I just showed you, hold it constant in time. It's a 2D model, so we're going to take that as a function of depth and then project it along strike. And then we're going to run earthquake cycle simulations. So here's an example of that. So this is what I was showing you before with the earthquakes occurring in the red colors. This is showing the evolution of shear stress. And this is showing time on the x-axis and then the maximum slip velocity in a logarithmic scale. So each of these large spikes here, that's an earthquake. So we're about to go into a large earthquake that ruptures the entire margin. So these would be like the magnitude 9 earthquakes, like the 1700 event. So that's the earthquake cycle model. Yeah. We have to make a choice about what type of friction. Is it velocity weakening or velocity strengthening? And so in this model, we think that we place that transition from velocity weakening to velocity strengthening at about 20 kilometers depth. And that gives us, it's most consistent with various data. So this shows you the different types of deformation and where they occur. So these are contours of slip. All of these panels are frictional slip. So this is a 10-meter contour of slip. This is one large margin-wide event, megathrust event. This is a smaller earthquake. This is another small earthquake. They're just in different colors, so you can see the different events. That causes, and that's occurring in the velocity weakening region. It transfers stress below that and creates what's called afterslip. So it's aseismic slip that occurs in weeks to months following the earthquake. And so in this case, you get another 2 meters of slip below this occurring as afterslip, for example. And in addition, we get interseismic slip, so relatively steady sliding that actually overlaps to a large extent, partially with afterslip. And then below that is where deformation is accommodated viscously. But you can see that there's an overlap of these regions. This is another way to look at it, where I've just put everything together, and you can see that there's some of this orange color in the region where we have both interseismic slip and afterslip. So actually, there's multiple deformation mechanisms at the same depth. I'll just say it here. And this is very different than regular earthquake cycle models where it's only friction. We go from velocity weakening to velocity strengthening. This shows you the partitioning of deformation, and in particular, look at afterslip. So in this frictional viscous model, afterslip is very limited in depth. Down here in this model, afterslip goes to really, really large depths. And afterslip occurs, it's very large after the earthquake and then decreases in time. And this viscous deformation is extremely steady in time. So it makes very different behavior that can be seen geodetically that allows you to discriminate between these two different models. There have been some reports in some subduction zones of deep afterslip, but it's somewhat controversial. So the models are making predictions that I believe will help test between these. Now, what about slow slip events? We they occur in this depth. ETS is episodic tremor and slip. And so we need a way to make, and we think slow slip events are frictional. We need a way to introduce friction in this region. And our previous model didn't do that. There's two ways to get more friction in this region. One is by having fluids come up to the moho, the interface with the continental crust, and then move upwards. And there's some reasons to think that that might be the case due to the permeability of the mantle wedge corner being very low. So that model will it'll change the fluid pressure and make it more, weaken the frictional strength and create friction there. Another way to do it is if we have a low permeability zone, just up dip of the mantle wedge corner. And that can happen if there's precipitation of silica in that region. So these are models that are in the literature, and both of them do produce friction in the region of episodic tremor and slip. Now, the problem with slow slip events, I think, is even if we make it frictional through one of these mechanisms, we usually think at these high temperatures at depth, the friction here is velocity strengthening. And so we shouldn't have instabilities, frictional instabilities that would create slow slip events. That is the most widely used model, but you have to go velocity weakening, velocity strengthening, velocity weakening. And there's not good evidence in the laboratory, I think, to support that. So my group's been looking at another mechanism called fault valving, where we change the strength, the frictional strength, not by changing friction coefficient, but by changing fluid pressure. And so here, what I'll argue is that, in the modeling, I think, demonstrates the possibility that we can have pulses of high pressure, pulses of high fluid flux that occur episodically in time, and they create slip, slow slip, so slow slip events. There's geologic evidence that pore pressure changes over the earthquake cycle. And there's also laboratory evidence that rocks at these depths have velocity strengthening friction. And we found that this fault valve mechanism also occurs with velocity strengthening friction. So I'll show models. These models this is sort of a different line of research. Everything's coming together, but not quite yet. So these models are friction only. So we'll use the same permeability evolution model, but not steady state. So now we're going to have this time-dependent evolution of permeability with the permeability increase with slip, decrease with healing. And it turns out it will produce fault valving events. Fault valving was an idea introduced over 30 years ago by Rick Sibson, and he showed lots of geologic evidence for it. So we did earthquake cycle simulations like this. This is not subduction zones. This is a vertical fault. I'll play a movie here. You'll see a bar that goes across and marks time. But this panel will show slip velocity in a logarithmic scale. So it's sliding faster here, slower down here. This is permeability, so low permeability, high permeability. This is fluid flux, right? It's high flux above that. And this is effective stress, which you can use to look at changes in fluid pressure. And what we discovered is that even though we're putting fluids in the bottom at a constant rate, we have permeability cycling, pressure cycling, fluid flux cycling, and the changes in pressure and normal stress create changes in strength, which create changes in slip velocity. So these are fault valving events. They're these slow slip events that propagate up in the direction of fluid flow. And they occur in this model periodically. That pulse of high pressure gets into the seismogenic zone and it triggers an earthquake. I'll play it another time here. So these are the fault valving events, right? So, oops, I guess it's not. Okay. I'll show you how this plays out for subduction zones. So we did a subduction zone model, so just a dipping fault, 15 degrees dip. We have, and I'll show you just one model where there's a constant fluid flux, not all the dehydration reactions, but we have done that too. I'm going to show the results in this type of diagram. This is depth along the plate interface. This is time, so space-time plot. And the color is showing slip velocity. So the fluids are released here at about 40 kilometers depth. They're coming up along the fault. This upper part is velocity weakening. This middle part is velocity strengthening. We have large earthquakes that occur, almost instantaneously, so you really can't see them here. This is a large megathrust event. Each of these red stars, that's an earthquake. Most of them are at the bottom of the seismogenic zone, but some of them occur in the middle too. But what's really interesting is that even in this velocity strengthening region, we have slow slip events. And they're occurring through this fault valve instability mechanism. And they're approximately periodic. They introduce a few centimeters of slip. Recurrence interval is about a year. So they're very similar to slow slip events that we see in Cascadia. And we varied various parameters. And so we understand some constraint, how differences in permeability and healing and other things influence this. But I think this modeling shows that there is a possible explanation for slow slip events, that it's not just velocity weakening friction, it's occurring through this fault valve mechanism. I think I will stop there. So in this talk, I've shown you, tried to emphasize the importance that in earthquake modeling, we need to also model fluid flow and pore pressure, which requires thinking about geology and petrology, the chemistry of it and what rocks are there. This frictional viscous transition, it's dynamic. It's not just friction and then viscous. It's really, in some regions, both, and they can occur at the same time or at different times in the cycle. There's a way to test whether you have velocity strengthening friction or viscous flow. In particular, by looking at responses to stress changes, something that we unfortunately don't have in Cascadia, and then offered a new idea that, or at least models that have helped test some ideas that have been out there, this fault valving mechanism for slow slip events. And I think it resolves some of the issues that we have with current explanations for slow slip events. Right. Thank you.